So let's get started with the week 10 assignment of NPTEL course VLSI Design Flow RTL to GDS. It's been conducted by Triple IT Delhi, Sneh Saurabh sir. So I'm going to present my solution for week 10. So please follow. So the first question here is, what is the controlling value? Controlling value for various gates. Controlling value for 2 input NAND gate, 2 input OR gate, 2 input XOR gate is being asked. So what does a controlling value means? So a controlling value when applied to a gate, what will happen? There is a logic gate and we apply and suppose there are n inputs. And if any of the value becomes a controlling value, then the output can be determined. Output can be determined if we are applying any of the input as the controlling input of that gate. So let's see our options. If we have a NAND gate, right? If we have a NAND gate, then what will be the controlling value? So if we have a NAND gate, then we know that if any of the value becomes 0, then definitely my output will become 1. So in that case, we will say that 0 is the controlling value for the NAND gate. And let's see for 2 input OR gate, what will happen? What will be the controlling value? As you can see, in case of OR gate, if any of the input becomes 1, so irrespective of the value which are at the other pins, I can clearly say that the output will become 1 for the OR gate. Therefore, the controlling value for OR gate will be 1. And next, controlling value for a 2 input XOR gate. So actually, in case of XOR gate, we cannot determine the controlling value. Why? Because it does not depend on the only one pin. Like there is no particular value that can determine the value of the output. Suppose, let me give you the example for this. Suppose this pin have value 0 and this pin now can have 0 or 1. Like when this pin is having 0, then 0 XOR 0 will become 0, and this pin is, if it is having value 1, then output will become 1. Similarly, suppose this pin was having G1 and one time I am giving this pin value as 0 and next time I am giving it as 1. So it means that output will become, if this pin was having 0 and this was fixed at 1, so 1 XOR 0 will become 1 and 1 XOR 1 will become 0. It means that there is no particular value of any pin that can determine which, when applied, I can safely determine what will be my output. So there is no controlling value that exists for XOR gate. It happens only for NAND gate and OR gate. And NAND gate, the controlling value is 0, and for OR gate, controlling value is 1. And this is the statement written in option A and option B. So it means that option A is correct, option B is correct. So this will be the correct option, only A and B. Let's move on the second question. Now we have to determine in this circuit, G2 is G2 of this, the Y pin of this G2 gate, G2 underscore Y. This is the notation to represent this, the Y pin of any gate. Suppose I want to represent X1 pin of G3. So I would write this as G3Y. Okay. Now there is stuck at one fault present in this at this pin. So if this fault is like 1, so what we need to do, we need to sensitize this fault. So if we want to sensitize, then I have to derive a value which is other than the stuck at fault. So it means that I have to drive at this point value 0, okay, to detect this stuck at fault, and I have to propagate this value also. So if stuck at fault was present here, it means that output will be 1, and if stuck at fault was absent at this point, my output will be 0. So this is the notation that I am giving. 0, okay, 0 will be the value at this point if there is absence of the fault, and 1 is the value that is coming here, will be the value itself when the fault is present. Okay, and this This 0 is the value that is coming at this point when there is absence of fault, and 1 is the value which is coming at the presence of fault. This 0/1, I'm calling it as D. This is a notation actually which represents 0 is the value which is coming in the absence of fault, 1 is the value that is coming in the presence of fault, that we are getting at this point in the presence of fault. So this is the D. Now I have to propagate this D value to the output Z. What I need to do? I need to make this line value as 1 so that this D can be propagated, and this D and 1, and it will become D bar. Now if this now at this point actually we wanted to drive 0, right? If I wanted to drive 0 through an OR gate, what I need to do, both, this is the value I need to drive to sensitize this stuck at 1. It means that both the logic pins, sorry, both the pins C and D should have value 0. Then only my 0 can be propagated and my stuck at fault can be sensitized. And at this point I need to drive 1. 1 can be derived if any of the pins A and B are 0. Like any of the pins are 0, both can be 0, any of the pin can be 0. Like if A is 0, B is 0, yeah, then my output here will be 1. If A is 0, B is 1, then also my output here will be 1. If A is 1, B is 0, then also my output here will be 1. So actually there are these many test cases possible. This A B C D as 0 0 0 0 0 1 0 0 and 1 0 0 0. So now let's match the solutions. A B 1 1, no, this is not correct. 1 0 1 0 1 0 0 0. Okay, yeah, this is one matching here. Okay, this one is matching. 1 0 0 1, this should not match. 1 0 1 0, this is also not matching. 0 1 0 1, this is also not matching. 0 1 1 0, this is also matching. Okay, so 1 0 0 0, yeah, this is satisfying my criteria, and this is my answer here. Let's move on to the next question. uh, so we have to select the correct statement here. If the redundant stuck-at fault occurs, we cannot observe its impact on the logical functionality. Yes, this is correct statement. There was one example given in the lecture slide. If you can remember, the redundant fault actually help in the reduction of the circuit, and there is no test vector to detect the redundant stuck-at fault. So ATPG tool should not is not able to determine any of the test pattern to detect the random fault. So redundant fault. So the answers are A and B. So let me quickly show you the slides which is related to this question. It was discussed in the earlier part of this week. Week 10. Just a second. It was discussed before physical design. Mhm. Yeah, this is the case. Redundant fault based optimization. So this was the illustration of redundant fault. So if you go through this slide, what you will see is that this stuck at one fault. Let me explain it to you. Suppose this one here we have stuck at one fault. So what we need to do, we need to drive 0 to sensitize this stuck at one fault, and the value will appear as 1 itself when the fault was present itself. So let me call this value as D. Now I need to propagate this D to the output. What I need to do, I need to make this value as 1 so that this D can be propagated here. Okay. Now this is what here, this is a NOR gate. So NOR gate will be able to propagate this output when this value here will be 0, right? But what we are going to see, that since we need to sensitize this error, sensitize this stuck-at fault, so I will be driving this 0 here, right? So this 0 is drived here. So what will happen is that this 0, when the NAND gate will see its input as 0, it is going to give this output as 1. So actually it is contradicting my conditions here. And if I'm getting 1 here, so one if any of the input of the NOR gate is becoming 1, so definitely my output is going to be 0. It means my output is I'm not able to detect this fault at my primary output. So this is a case of a redundant fault. We cannot detect this output. So there is no test. This is written here, right? There is no test vector exists to detect this fault. So this kind of fault is called as redundant fault. Now, redundant fault can be used to reduce the hardware, and the redundant fault means that the behavior of the circuit with and without fault will be the same, and this is actually used to used to reduce the hardware. It is written here, right? This is what I was explaining. So there is no test vector available to detect that redundant fault. Now let's coming to our question. Yeah, this is our question, and it was saying the if a redundant stuck-at fault occur, we cannot observe is its impact on the logical functionality at the primary output of the circuit. Now you can answer this like this is a correct statement. And next statement is a redundant fault occurs. A redundant fault cannot be detected using any test vector. Yes, this is also correct. A good ATPG tool should be able to determine a non-empty set of test pattern. No, there is no actually test vector that itself can detect a redundant fault. Therefore, C option is not correct. So the correct statements are A and B. So this is my option. The BIST based testing, I'm going to question number 4. In BIST based testing, BIST means built-in self-test. That's what has been explained in the earlier part of the this week lectures. The compact circuit typically employ the to generate random test pattern. If you remember, sir has discussed this topic, LFSR, linear feedback shift registers. Linear feedback shift register. What it does, it has a kind of shift register as you can see, and there will be some OR gate formation between the flip-flops, and this is being given in the feedback to the flip-flops. In this way we are generating some random patterns. There is no there is no particular format with which it will generate. Like we can play around with the OR gate, and in this way we will be generating some random test patterns. So this thing is called LFSR. You can refer to the lectures. I can show you the reference from where this question was framed. As I told, it is done in the previous part of this week before the physical design was discussed. So yeah, this was the second lecture of this week. So let me tell you, yeah, this is one illustration for BIST test pattern generator, and it generates using a linear feedback shift register. As you can see, these are the feedback, these are the taps. When the taps are on, then this value gets entered into this XOR gate, and in this way we are going to generate random pattern. This was one example here. As you can see, if the example if my initial state suppose was 100 here, then what is happening, this pin, if you see, let me call this as flip flop 1, this pin as this as flip flop 2, this as flip flop 3, and the input of flip flop 1 as D1, output as Q1, flip flop 2 input as D2, output as Q2, flip flop 3 input as D3, output as Q3. Now the next state of this pin Q1 and then plus 1, and I am calling it as next state. It will be what? It will be D1. And what is D1? D1 is actually X1 XOR X 0. X1 XOR X 0. And what are X1 and X 0? What are X1 and X 0? These are A1 and A 0. These are A1. These are A1 and A 0. And what are A1 and A 0? A1 and A 0 are D2 and D3 itself. D2 XOR D3, right? So next state of Q1 is D2 XOR D3. Now other will be like the shift register part. So Q2 next state will be D2. And what is D2? It is connected to Q1. It is connected to Q1. Sorry, I wrote here D2. Sorry, it is not D2 XOR D3. It is not D2 XOR D3, but rather it is Q2 XOR Q3. Okay. So let me correct it here. It will be Q2 XOR Q3. And the next state of Q3 will be D3, and D3 is attached to Q2. So Q3 and Q3 next state is Q2. Now the outputs are written here as, I guess it is written here as Q1, Q2, Q3, right? Now you can do the this you can apply this one to get the next state of Q1. It will be the Q2 XOR Q3. So next state will be 0 XOR 0 means 0, and these things are just shifted, 1 and 0. 1 XOR 0 will become 1, and these are shifted, 0 1. 0 XOR 1 will become 1, and these are shifted, 1 0. 1 XOR 0 will become 1, and these are shifted. 1 XOR 1 will become 0, and these are shifted. 1 XOR 1 will become 0, and these are shifted. 0 XOR 1 will become 1, and these are shifted. So this pattern has this sequence has now occurred again. So there are how many sequence? 1, 2, 3, 4, 5, 6, 7. 7 unique sequence, and after that pattern is repeating. So it is kind of mod 7 counter, we can say, not a synchronous up or down counter. It is a counter which is generating, has 7 unique states, and after that is repeating its state again. So that's why I'm calling it mod 7. So these are the states, and these are random states. Okay, number of ones are here and there, and they are repeating itself. So it is a kind of a random sequence generator. And why we do that is, like, it has been observed that 90% of the stuck fault can be detected by using few less number of test vectors are required for that. There was one graph actually written, given in our slides. As you can see, less number, like 100 random test pattern itself are giving me very good accuracy. Like if you want 100% accuracy, definitely there will be thousands of random test pattern. But with a limited amount of test pattern also, I can get a very good fault coverage. I mean, fault coverage means many stuck at fault can be detected with a few random test pattern itself. That is the idea. So we are going to make this circuit LFSR, linear feedback shift register, to generate a random test inputs or random test vectors. So this actually helps us to generate random test vector, and it reduces our burden to store the large amount of this test vector. So in that way, I'm saving my cost in the memory, and I'm generating my random test vector. So this is the whole idea of LFSR. Again, now quickly moving to our question. So I hope this is clear now. Like in BIST based testing, the compact circuit typically employs to generate pseudo random pattern is LFSR, linear feedback shift register. Now moving on the fifth question. In BIST based testing, the signature of a good circuit matching the signature of a fault circuit is called. Okay, this process, what it is called? In built-in self-test, what we do, there is a signature of a good circuit. Like good circuit will generate some output, and we will work on that output and get some signature. Like number of ones, we will count number of ones. Anyway, once counting is not a very good method for a signature capturing, but just an example I'm giving. Like sir has also discussed this example. Like for a given test pattern, my output is having some number of ones, so I count the number of ones, that is my signature. So I now match this signature with the golden signature. Golden signature means which is a correct signature, the intended one. Means a fault free circuit would have that signature. So that process of matching the signature to test whether the circuit has stuck at fault or not, that is called aliasing. Okay, this has, let me show you the reference from which this question was framed. Let's go there. Yeah, it's just before the physical design part has started, I guess. Mm-hmm. Yeah, this one. Yeah. As you can see, during testing, it is possible that the signature of good circuit and faulty circuit should match. If they are matching, good circuit, circuit of good, sorry, signature of good circuit and faulty circuit are matching, then it is called aliasing. It is not a good thing actually. Why? Because a faulty circuit should produce a different output, and a good circuit should produce a different output. There should be a difference in the output. Then only we can say that my circuit, then only we are able to detect actually that the circuit is fault or not. Okay, so aliasing should not happen. It's not a good thing. So signature of good circuit and fault circuit are matching. This is called aliasing. This phenomenon is called aliasing. Moving on to our question discussion. Okay, so aliasing is the option. Aliasing was another option, and I take that option. So this is the solution for question number fifth. Let's go to the sixth question. A metal interconnect line in an integrated circuit has a sheet resistance of 0.08 ohms per square. The length of the interconnect is 1 micron and the width is 0.01 micron. What is the resistance of the interconnect? Okay, let's see here. I'm trying to draw it so that you can get a better idea. Okay, let's do that. So what is given in this question? So actually, sir has taught in this lecture that there is a thickness parameter that is predefined in the foundry. In the interconnect means the copper wire that we are going to interconnect between the various layers so that we can connect the all the device part. That is the whole idea of giving the BUL, the back end of the line. The front end of the line contains the device layer, and the back end of the line contains the metal layers. And the whole idea of metal layer is to give the proper interconnection between all the circuit elements. So interconnects means they are actually wire itself, copper wires. Okay, they have good conductivity and abundance. So the thickness of this wire is actually predefined. Okay, it is predefined. So as a designer, I can only deal with the width. I can only change my width and the length of that interconnect of the wire. Like this is the length and this is the width, and these are in my control, but the thickness is not in my control. This is given predefined. I can't do anything about it because the foundry will decide. Now, what is given here? The sheet resistance of Ah, the metal interconnect line in an integrated circuit has a sheet resistance of 0.08 ohms per square meter. Okay, RS, sheet resistance. RS, if you remember, it was actually rho upon T. Rho upon T means resistivity upon T. Resistivity is predefined value of any material. Copper has predefined resistivity. T, that is the thickness of that sheet, thickness of this interconnect that we are going to make. It is also predefined with the foundry. So rho by T, that is also predefined here. So this value is given as 0.08 ohm per square meter, or anything you can write. Ohm per square. Okay. Ohm per square. Okay, I'm leaving it as square only. Square units. Okay, fine. And the length of interconnect L is 1 micron. 1 micron means 10 to the power minus 6 units, length units, whatever it is. And width is 0.01 micron. So this W is 0.01 into 10 to the power minus 6 units. So you can write it as 10 to the power minus 8 units. Now, what is the value of resistance? What is the resistance? Recall your basics that you have studied in uh, uh, before coming to college itself. The resistance value, it is rho L by A. Very basic, guys. So rho here is the resistivity is resistivity. No change in that. L here will become this length L. And area, if you see, area is how much? Area is how much? This area we are talking about, because this is the area through which current will be flowing. W into T. Now, if you see rho upon W, and this value is predefined. L by T. This value is given actually, the sheet resistance. So here in this case, R will become RS times L upon T. And the question is asking us to find the resistance of the sheet. So R will become this RS, which was 0.08 ohm ohms square centimeter, that's square units. This whole thing multiplied with uh, L upon T. L value was 10 to the power minus 6 units, and this T value, the thickness was sorry, um, I did a mistake here. Let me correct it. Mm, okay. This rho upon t value was defined as Rs, and this is W actually. This is W, and W value is given as, yeah, W value is given as 10 raised to the power minus 8 units. So I will get the answer as 0.08 times, this will become 100, and it will become 8 ohms, right? So this is my solution here. Okay, rho L by A will become units, uh, L by W, rho upon T. Yeah, yeah, this is what I am getting. Guys, I was wondering like why my units were not matching. The given unit was ohm per centimeter square, or square units, and the this unit of L by W, it was cancelling each other. So the answer was coming having unit this much ohm per centimeter square or per unit square, whatever that was. So I checked this formula. This R is rho L by A. So if you see, rho is having unit of, will be having unit of, let's quickly uh, remove this confusion. This rho is having unit of R A by L. So A has unit of centimeter square, is having centimeter, so it is ohm centimeter kind of unit, right? And when you divide this with some length unit, like resistivity divided by the thickness of the thickness of the interconnect. So thickness is having a unit of centimeter, then this rho upon t, this will give you unit of ohm itself. So I think it is a mistake here. The value of the sheet resistance will be in this much ohm itself, 0.08 ohms. It should not, unit should not be per square. So then you will get 0.08 ohm, and this is unitless quantity, and finally you will get the value as 8 ohm. So this will be the solution here. Let's move on to the next question. Consider the following statement which are correct. Okay, correct statement. In dual Damascene, Damascene, whatever it is, Damascene process is employed to fabricate layers of copper interconnect during IC fabrication. Yes, this is a correct statement. As you can see, in dual Damascene process, what we do, we try to give the copper interconnect in such a way, like this will be the formation. One wire will be going in this direction. Suppose, let me draw a coordinate system for your understanding. X is X and Y and Z. So suppose a wire is running in this Z direction, and other wire is running in X direction. Okay, and then there is an interconnect in between them. So this is a dual Damascene process, is a process to employ the is employed to fabricate layers of copper interconnect during IC fabrication. Yes, this is a correct statement. And ion implantation is employed to dope the semiconductor with required dopant. This is also correct statement, that we have this was done to make the MOSFETs. We do ion implantation. High velocity ions are bombarded into the silicon, and then with the process of annealing, they capture or they acquire the silicon places, and this way n type and p type semiconductors are being formed. This is the modern day method to create the doped silicon, the doped n type and p type materials. And shallow trench isolation deposits a uniform interconnect metal layer during ice fabrication. No, we do not deposit a metal layer. The whole idea is that the n region and p region of the MOSFET, they do not interact with each other. And to stop that interaction, what we do, we actually increase the trench. We increase the trench means the silicon oxide layer will act like a barrier between these regions, this charge region, and they will not try to interact with each other. So I will show you the reference from where I am getting this idea. This was discussed, I think, in the starting of the week itself, first lecture of this week. This is this one we are talking about here. So this is suppose P-type substrate. This is N-well and P-well. So this is the trench I'm talking about, shallow trench isolation. And this itself is what material? This is a SiO2 gate material only, silicon dioxide. This material we are having, this is oxide layer, and oxide layer is being trenched, is a dig deep inside these two wells, and they will not interact with each other. That is the idea. So this is a this is not definitely a metal layer, right? This is an oxide, this is a insulator kind of thing, which is trying to avoid the interaction between these two wells, N wells and P wells. Okay, this is the intended purpose. Let's go to our question now. Yeah, this was all my question. So shallow trench is not a method of depositing a metal layer. It is indeed we deposit an oxide layer to avoid the mixing of N well and P well, and because that will destroy my whole device itself. So this is not the correct option. My correct option is dual demasking process employed to fabricate layer. Yeah, this is correct, and implantation is to employed to dope the semiconductor with required dopant. This is also correct. So correct option are only A and B. Moving on to the eighth one. Consider the following statement about the signal integrity issue of glitches used to convert use glitches due to the two interconnect lines running on parallel tracks. Yeah, this is what I was discussing now. Two lines running on a parallel tracks, but they are like coplanar. They lie on the same plane, but they are actually perpendicular to each other. But still they are planar, parallel. Why? Because they will not intersect each other at any point of the time. So signal integrity issue will become more prominent when the two lines are closer. That is correct statement. Why? Because if the lines are closer, then the effect that is happening on one line is going to affect on the victim line. Suppose I am calling this as aggressor and this as victim. If they are closer, so they will do crosstalk, means the fluctuation having here in the aggressor will cause victim to get affected, and then it will become more prominent if their lines are closer. So this is a correct statement. Now the second statement is the signal integrity issue will become more prominent when the slew of the aggressor line increases. Now see here, like if the slew increases means my signal is rising gently. I mean it is not rising abruptly. And if the signal line is increasing slowly, then what will happen is that the charge deposition on the coupling capacitor between the two wires that are going to crosstalk, the charge deposition will be slow, and the voltage developed across the capacitor will be slow. It means that there is a less load on the driver gate to provide the charge to this capacitor. So it means that I am not going to see the bump in the victim line, right? So that is the whole idea. If the slew is less, the less abruptly the signal is changing, then there will be less chances of getting this bump less chance, less bump. So signal integrity issue will become more prominent. No, signal integrity issue is becoming less prominent actually when the slew of the aggressor line increases. If the slew is decreasing, then it will become more prominent, this issue. So this is not a correct statement. The signal integrity issue will become more prominent when the strength of the driver connected to the victim line increases. So if the strength of driver is increased, then it is going to fulfill the demand of the coupling capacitor. And if the driver is strong, then the demands are meeting, then we are going to see less signal integrity issue. But here it is saying that signal integrity issue will become more prominent when the strength of the driving is increasing. So actually this is contradicting, right? What is the actual concept? So it is becoming less prominent when the strength of signal is increases. It is written as more prominent, so this is incorrect statement. So the correct statement here is this first statement only, that signal integrity issue will become more prominent when the two lines are closer. So the correct statement will be only one A. Going to the ninth question, which of the following file is typically given as an input to physical design implementation tool? Actually, this was LEF file, the library exchange format, and there are two types of library exchange. One was related to technology and one was related to cell. Technology was something which was defined by the foundry itself, like the width of the thickness of the interconnect lines is one example. So see, these kind of things are written in the technology library, and the sheet resistance. Okay, and there are cell library related to what kind of cell we are going to use, what will be the intrinsic capacitance, and all these kind of things are in the cell library. So LEF, library exchange format, that is going to take into account for the physical digital and implementation tool. The other options, let's look at that. PDF file, no, PDF file means this PDF file that we use in day-to-day life, portable document file or something like that. VCD is a synopsis tool. It is used for I guess Verilog purpose, means RTL designing purpose. And CPP is your extension that we give to store the C++ files, the programming language C++. So anyway, so for the correct option for our case, physical digital implementation tool is LEF file, library exchange format. Next, which tool is used to perform the physical design task? Clearly, the answer is OpenRoad. Very much clear here. OpenRoad is my answer. It is a tool that we use to perform physical design tasks. Let's look at other solutions. Uses Icarus and VCS. Icarus is Icarus Verilog, doing for RTL things. VCS, sorry, I told this VCD. Okay, VCD is value change dump or value coded dump, something like that. So if you have done your if you have done your spice simulation and all, then you will know that a VCD file is generated to dump the value. We generate a VCD file to whatever simulation result we are going to get, and we dump it in the VCD file. So yeah, this is the thing. But this is not a physical design tool. Okay, and the OpenRoad is a design tool to perform physical designing task. Yeah, this is correct. VCS is the tool actually by Synopsys, and VCS is used to perform on the RTL or designing related part. Icarus is open source software. Icarus Verilog, if you have, I know most of you will be aware of this thing. Icarus Verilog is a open source software for the RTL designing thing. And USYS is used to get the gate level netlist of for the given RTL tool RTL code that I have written. So this is the thing. So the correct option is OpenRoad. So this ends our discussion for this week 10 assignments. I hope you got all the solution. If you have any doubt, please comment. I'll be happy to answer. Thank you.